Good morning. We are starting the second industry workshop on asphalt pavements. First, I would like to invite Professor Gabriele Tebaldi and Professor Eshan Dave to begin with the presentation. Professor Tebaldi and Professor Dave are the chairman of the TC 264 REP.
Thank you very much, ladies and gentlemen, to be here for this. That is the second industry workshop under the activity of technical committee on asphalt pavement recycling. But before to start, I would like to invite Liedi, because on behalf of the RILEM TC REP, and I can say on behalf of RILEM in general and also of our community, we would like to recognize Liedi, because she is the first woman that is a dean of the Politécnica School of São Paulo. So please, we have a small present for you to recognize this.
Maple syrup from New Hampshire.
Thank you very much. It's very kind.
And also we would like to say thanks to Camilla that took care of all the logistic arrangement, and so we have also a small present for New Hampshire. So if you like pancake, you can enjoy it. I have to be really honest, Liedi, it was my wife that made the choice. I cannot take the right. I'm only a poor pavement engineer. It's not in my skill. Yeah. So, again, thank you very much to be here. As I said, this is the second industrial workshop that we are organizing under the activity of the TC REP, that is dealing with the recycling of REP in different way and all the aspects. We believe that it is important to have event and workshop like that, because we would like, from one side, we would like to disseminate our achievement and what we are learning, but from the other side, we believe that it's extremely important to have your point of view, because we are in the academia and we enjoy to study mechanics, other things, but we strongly believe that we have to serve. Our first duty is to transfer knowledge. So it's important to know what the industry world, the agency and the consulting needs to do their job, because we have to work to find the solution for their problem, or to give them the knowledge that they need to face the day-by-day problems that they have in the work. So it's extremely important for us to have your feedback, to learn from your question, and to receive, why not, your criticism or your comment, because in that way we may address our attention on the problems that really need to be solved, that really need an answer to make simpler and most efficient the work of the industry and the agency. Some time ago I had to write an editorial for a journal, and I was remembering an old Chinese philosopher say that even a 1,000-kilometer journey start from the first step, But as a pavement engineer, I like to say that it needs a good road. Otherwise, you cannot go anywhere. And this is the reason because I think we are here today. So now I think that we may start, and we can go ahead with the two different topics on recycling, hot and warm and cold. Thank you very much again.
The first presentation today will be held by Professor Liege Bernucci and Professor Camila Vasconcelos. Professor Liege Bernucci is a civil engineer, Master of Science in Geotechnics, Doctor in Transportation Engineering, full professor for Infrastructure and Transportation Engineering at the University of São Paulo since 2006. She has been the head of the Laboratory of Pavement Technology since 1995. She was elected Dean of the Politécnica School of the University of São Paulo in 2018, first woman that holds this position in 124 years. Professor Camila Vasconcelos is a professor in the Department of Transportation Engineering of the Politécnica School at the University of São Paulo, in which she has been working in pavement materials studies. She is an editor of the Transports Journal in Brazil, the coordinator of the task group Asphalt Binders Performance of the Brazilian Institute of Petroleum, Gas and Biofuels, IBP. She is the vice coordinator of the task group Degree of Binder Activation, TG5, of the Technical Committee of RAP TC 264 of RILEM. Please welcome Professor Vasconcelos and Professor Bernucci.
Good morning. I'd like to thank the invited speakers for coming, and also to thank our sponsors, Kraton, Ingevet, Betunel, Fremix, and Aberto Chairs for the financial support. Ladies and gentlemen, it's a pleasure to have you here, and welcome to Politécnica School of the University of São Paulo. Just a little bit about Brazil. Brazil has an area, I will change the microphone. Brazil has an area of 8.5 million square kilometers and a population of over 208 million inhabitants. The total extension of roads is 1.7 million kilometers, and only 211,000 kilometers are paved. And which represent 12.3% of all paved roads, all roads. Okay. Brazil has only 25 kilometers of paved roads per 1,000 square kilometers, which is much less compared to other countries comparable in size, like the U.S. The United States have almost 18 times more paved roads than Brazil. It means that we need more roads, new roads, more construction, and maintain the existing paved roads to increase our economic growth and our social benefits, and also to become more competitive. The state of São Paulo has 15 to 20% of all paved roads. And also, we have the highest amount of toll roads operated by concessionaries. Oh. This is the state of São Paulo started recycling in the 80s, and this is the first hot asphalt recycling site in Rodovia Anhanguera. This is a very heavy traffic road. We can see the photos, the old photos, the plant and so. They used 50% of RAP, reclaimed asphalt pavement, the old material, and of course 50% of new materials for the surface layer. And we can see also here the construction site. This experience lasted 16 years in good condition. And our master student, Castro Neto, used this experience in 2000 to propose a method of a hot recycled asphalt mixture design. And he determined the amount of asphalt rejuvenator, measuring mechanical properties such as resilient modulus, indirect tensile strengths, countable loss of weight. The first work on cold asphalt recycling was done by Marcandali da Silva in 2011. She used an experimental track built in a very heavy traffic road, Regis Bittencourt, using emulsion. This is the set of machines. This is the material, cold recycled material, and this is the cold recycled layer being constructed. They covered this layer by a very thin layer of asphalt concrete. This is our first work on warm mixed asphalt done by Mota in 2011 in her doctoral thesis. And she compared warm asphalt mixture to hot asphalt mixture, and this is an experimental track in a very heavy traffic road, Rodovia dos Bandeirantes. And then this study led us to research the warm asphalt recycling technique, but for RAP, adding RAP. Professor Mota and Marcia Takahashi, in another investigation in 2013, they measured the HPA's emissions, and they compared warm asphalt mixture to hot asphalt mixture. And we can see that warm asphalt mixture has less HPA emission than hot asphalt mixture. They measured in the lab, in the field, and also in the plant. Then hot asphalt recycling led us to study warm recycling and also cold recycling of asphalt mixture. And we continue our technological applications, and also we are researching to form more comprehensive understanding of behavior and this is our contribution for the academy and also for the industry. Thank you very much. Professor Camila will present our ongoing research. Thank you very much.
Good morning, everyone. Thank you for being here today. It's a pleasure to have this room almost full of people from universities, industry, agencies. It's very nice for us to hold this event here at USP. I'll try to summarize the ongoing studies that the Laboratory of Pavement Technology, the studies we are doing. We have several students working on recycling nowadays, on cold recycling and hot and warm recycling also. So the presentation I divided in cold recycling and hot and warm. Let's start with the cold recycling. The first study, it's been done by Frederico. He is a PhD student, and the idea of his study is to better related to cold recycling, we still have a lot of discussion on the behavior of this type of material. We have Professor Kim here from University of Stellenbosch in South Africa. They have been working on cold recycling for many decades, and they see these materials as like an unbound material with high cohesion. In Brazil, we have some experiment following the same trend or the same way we see this material, but also some cold recycling techniques with more foamed asphalt or more emulsion and more activate filler, bind cement or hydrated lime. So in Frederico's study, we'll more follow what South Africa they have been doing. There is one specific test, the monotonic triaxial test. Is not so common in Brazil yet. So we, as part of his study, we will get more information on this test specifically for different materials. That's part of his study. Also, we are going to have some field experiments. I've put here 3 different sections. 2 of them already constructed and under evaluation, and another one that is supposed to be constructed this year. So the idea, the main idea of Fred's study is to get some performance model for this type of material, cold recycling with foamed asphalt. The second study, it's from Kazu, is our master student. He should be done by the end of this year. In his study, he will try to understand better the stiffness behavior of cold recycled mixtures. Not only the ones with low binder, but also the ones that have a little more hydrated lime or cement on it, since we have a couple of test sections using more cement. So in his study, he will try to get the influence of temperature on this material, the influence of moisture, more specifically, what exactly is going on during the curing process, when water is getting out of the material in the lab and in the field, what exactly happens. And also the confining stress. So the third study is conducted by Vanderlei. He's right behind here. He'll be also working on cold recycling. I've put here the 4 test sections already constructed and under evaluation. And what we see here is these 2, one with emulsion, the other one with foamed asphalt. But this one, they have 2% cement, a little more binder than what is established by South Africa. And it has 12 centimeters of HMA on the top. The other 2 structures, they are on the same highway, but also now I have just foamed asphalt, in one side wrap, and the other one, the virgin aggregates. But on the top, I have just 3 centimeters. So this type of sections is more similar to what is being done in South Africa. So the idea is, okay, if we assume that permanent deformation is the main distress on these structures, how we may evaluate, and we selected the flow number test. There is a test for HMA. So that's the first standard here, using stress of 200 kPa and temperature of 60 degrees C. But we are going to also test different conditions, test conditions, in terms of temperature and in terms of stress. So the second scenario, we are following the recommendation of another publication with less stress and less temperature. And the third condition is simulate in a 3D software what is going on these structures and try to get that on the test. The fourth one is related to code recycling with emulsion. This test section is in Castelo Branco Highway. It's already constructed, done by Wilson Unger. He is a student of Professor Rosângela Mota. And in the lab, he's studying the compaction method, the storage time, and the curing time. In the field, he'll keep the monitoring of the test section. Here is a picture of the plan that was used in this job site. Going to the hot and warm recycling, this slide here, it's from a former student. He's not in the lab anymore. Manuela has done his PhD and also postdoc at the Laboratorio of Pavement Technology under the supervision of Professor Liege Bernucci. Manuela's study was very broad because she worked on the binder, on the mix, and during her postdoc, he got also the field test sessions with 8 different mixtures. In Brazil, we face, I cannot say a problem, but it's very difficult nowadays to go up to 20-25% of REP in the hot recycling. So in Manuela's study, he went up to 25. He had hot and warm, and also with neat binder and polymer modified binder. So all the test sections are performing very well right now, until right now. And I've put this protocol here because during our meeting yesterday, the RILEM meeting, we discussed a little bit about what exactly happens with the binders when you mix the binder from the wrap with the new binder. How does it blend? How do you activate this binder wrap? So in this case, Manuela tried to qualitatively identify where was the aged one, where was the new one with the FTIR. So I think it was a very important part of her study. I've talked to her in the last 2 days, and she mentions that another student in France kept the same trend, but trying to quantify this blending with the FTIR. Another study that it just started this year, it's been done by Zila Mascarenhas, also a PhD student, on multi-recycling. It's not an actual issue in Brazil because we are still trying to keep going on the first recycling. But if we recycle today, in 10, 15 years, we might want to recycle this mixture again. May we really get back the performance of this recycled mixture 1, 2, 3 times, or how many times can we do that? So this is part of Zila's study. She'll keep her eyes on the binder, but also on the mixtures. I don't think we'll be able to do anything in the field related to multi-recycling yet. The other study, it's been done by Karina as a master's student. Karina, she has mostly lab results, trying to increase this amount of REP on the mix without and with recycling agent. But Karina is also, she works in a concessionary here in São Paulo, so she is also trying to put this mixture in the field. So she has done a very detailed literature review on what should we change on our asphalt plants to be able to really recycle these asphalt mixtures. So in Brazil, we are trying to stay here, at least at this first moment, but it would be very nice if we could have asphalt plants prepared to go in higher amounts of RAP. Another study, this is Caio. He is also a master's student, and his study is looking, okay, we have some different types of asphalt mixtures, and we know that. And one of them is we call SAMI here in Brazil, stress absorbing membrane interlayer. That's the most common name. We've been calling strain relief asphalt mixture. So that is one job site in south region from Brazil. And what we're trying to reach is, okay, may we also put RAP on this type of mixture or not? Caio's he's looking much more on the binder side, but he will also check asphalt mixture in terms of fracture mechanics. So this study is also being done in our lab by Márcia, master student. This one is not only related to recycling, but it's related to aging. So on the binder side, we try to understand this aging process in terms of physical, chemical, and rheological measurement, trying to use different binder sources, chemically speaking, but also different rejuvenators. I guess this is the last one. This has been done by Mateus. Mateus is also a master's student. I've mentioned the degree of blending in some previous slide. Mateus is trying to quantify this blending. Okay, we are going to mix the binders anyway in the lab or in the plant. How can we quantify if this binder is really homogeneous or not? So in his study, we are doing staged extractions, but trying to follow a standard procedure, an ASTM procedure, and use rheological and chemical parameters to get on this DOB, degree of blending. As the final remarks, I divided also on two separate boxes. Related to cold recycling, I guess Brazil, it's advanced in terms of techniques, in terms of application, in terms of equipment. Materials behavior, we know now that it's highly dependent on the mix composition. So if you put more cement or more hydrated lime or more binder, you may have completely different materials. So say only cold recycling is just too broad. Material and pavement performance, they must go together. If you are designing your pavement, you have to make sure you know exactly what type of mixture you are thinking for this place or this field, this pavement. And we still need some performance models. We are in touch with Professor Kim Jenkins. He just finished the advising of a student with a performance model for South Africa. We may try to calibrate for the Brazilian conditions. The fact is, the agencies, sometimes they don't want to approve a project because we don't have the models to predict how much time it's going to last. It's fair. So if we end up having some sort of Brazilian model that we could use in our projects, I guess it would make it easier for the agents to approve this. Regarding hot and warm recycling, we definitely need better asphalt plants. Otherwise, we will always be limited to the amount of REP that we can put on our mix. We have to have more care with the REP handling, because if we decide to use in the hot mix asphalt, as part of the hot mix asphalt, we have to know what we are putting in there. We also need to improve mix design, understand the use of rejuvenators on this plant. But maybe the most important final message, we are pretty sure we can do more, we can do better if we keep working together. RILEM is a very nice opportunity for that. I keep saying to my friends, my colleagues, that after I entered RILEM, everything changed, because I know much more people now, I know what they are doing, we keep in contact, we discuss different points of view, what I think is very productive. So I think that's it. Thank you very much for all the sponsors, and I hope you enjoyed the day.
We have presentations on the topic hot and warm recycling. First presentation is by Professor Paul Marsac. Dr. Paul Marsac is research engineer in the French Institute of Science and Technology for Transport, Development and Networks, IFSTAR. He works since more than 30 years on bituminous materials, in particular on the characterizations of their mechanical properties, notably complex modulus and fatigue resistance. Paul is currently conducting research on recycling, and especially the effect of multi-recycling in its combination with warm mixing process on the durability of the asphalt mix's properties. Paul is the chairman of the French Commission for Standardization of the tests related to pavements and in charge of the TG2 non-cold recycling of the RILEM TC264 REP. Then we have the presentation by Dr. Martin Hilsner. Dr. Hilsner is a senior researcher at the Laboratory for Road Engineering, Sealing Components of EMPA, Materials Sciences and Technologies in Switzerland. His main research topics are bituminous binders and recycling of asphalt pavement materials. He is active in European standardization of bituminous binders and the leader of RILEM TG3 on asphalt binders and additives of TC REP. Dr. Augusto Falchetto is an assistant professor in the Department of Civil Engineering and Environmental Science at Technische Universität Braunschweig in Germany. His main research interests focus on material characterization, modeling, and scaling. Dr. Falchetto is active in different committees of RILEM, ISAP, and TRB.
So good morning. So it's a pleasure to be here at the University of Sao Paulo. And I must add that I'm not a doctor, nor a professor. I'm just a research engineer. So you could skip to the presentation. Yeah. So I will try to summarize the works of the RILEM in the works of the RILEM for in hot recycling. So the aim of the TG I will show is to characterize RAP. Yeah. So I can, maybe we can skip to...
We might have to invert the order of the presentations because we have to switch the file. Let's go for the second one, rejuvenators for asphalt recycling. That is going to be presented by Martin Hugner and Augusto Falchetto.
Okay, thank you very much. I hope, yeah. I also need my presentation, actually. I will talk about rejuvenators, although I have learned that in Brazil there is not such a lot of recycling yet. So, but maybe in the future you need these too. So, okay. Why are we using rejuvenators in hot recycling? This is especially for hot recycling. You know that the recycled asphalt pavement, the old material is getting hard. So if you want to use it in a new hot mix, we have to make it softer to rejuvenate this material. And there are several options. Normally you just add a softer binder. And if you mix it with the old material, you get a softer or what you normally get, the binder rheology, what you have in a hot mix. But that works only up to about 50% of a wrap, what you can add. If you go higher, then you have to add an even softer binder, and somewhere you get... there is an end. You don't have any binders which are soft enough. So there you have to add some rejuvenator to decrease the viscosity of the mix. So what are these rejuvenators? This is not a really easy question because the chemistry is very different, because the sources of the rejuvenators which you use for making them are quite different. You can make rejuvenators from mineral oil like the bitumen, or you can use some plant products like vegetable oils, which is maybe too expensive anyway, or other industrial byproduct. Actually, the sellers of these rejuvenators are very ingenious. They can sell a lot of things, and you have to be careful what to buy. Actually, it's not only the viscosity which is important. It's not. You cannot just decrease the viscosity of the binder. You have to look at other things. But how can we find out what is a good rejuvenator and what is a not so good rejuvenator? There is an interesting study made in Germany, where they compared quite a lot of different rejuvenators which were on the market. So you see here, this is these are results from DSR measurements, and you see the black line is the wrap, the old material, and the blue region is actually what you have normally for a virgin binder. So actually, what you want is that if you add the rejuvenators, you would like have that the mixture would be back here. And actually there are some rejuvenators which can do that, but a lot of the rejuvenators just move on this line again, which is more or less just reducing the viscosity. Or there are even some which are going in the opposite directions, which actually you don't want. So there are other criteria, and we are still struggling a little bit. What is the right criteria, the right method to assess the method, to assess the quality of rejuvenators? actually, we have also to look a little bit about the aging of the bitumen to understand why we can use these rejuvenators. Because actually you can divide a bitumen in different parts, which is normally called the thorough fractionation, which divides the bitumen in 4 different regions, which are the saturates, aromatics, resins, and asphaltenes. And if you look at the aging, for example, in RTFOT, short-term aging, you see that the saturates and the aromatics are decreasing in the amount, and what is increasing are the resins and the asphaltenes. So actually, what you could think actually quite easy. So you only have to replace the saturates and the aromatics, and then I have again my new bitumen. But this is not so easy because you need quite a lot of these saturates and aromatics, and normally you add not such a lot of rejuvenated quantities. It's about between 5 and 10%, depending on the amount of wrap. So that's not actually possible. You also have to divide between different kind of aging. We are talking about physical aging and absorption of maltanes. This you can somehow revert if you add some of this. But for example, the chemical aging, which is the oxidation of some double bonds which are in the bitumen, this is not possible to revert. So actually, it's not possible to revert the aging completely of a bitumen. So my conclusions are some agings are actually reversible, some are not, especially not the oxidative aging. So chemically, a rejuvenated bitumen is never the same as a virgin bitumen, because you have always these aged parts left inside. However, the question is this really necessary? Because, bitumen is a really complex mixture, and it's not necessarily said that it's the best mixture. You know that you can add, for example, polymers to increase or to make it better. So maybe you can also make it different. But probably rheologically, rejuvenated bitumen can be almost identical, at least in the beginning. But one important point is the aging. And this is actually exactly what we are doing in our TG3. We are looking at the aging behavior of such mixtures between rejuvenators and bitumens. We have not yet any results, so you have to wait a little bit. So I give over to Dr. Falchetto.
Okay, good morning. I will start from where Martin left. So I will show you some result of a study that was performed at TU Braunschweig in Germany. It's a very simple experimental study on the possibility of using rejuvenator in combination with reclaimed asphalt pavement. And as I said, as an experimental study is based on a simple and, let's say, new test that was proposed in Germany, which is the bitumen TP0 Schnellverfahren, or actually in English, binder fast characterization test, and on a series of conventional tests on asphalt mixtures. Okay, what did I do wrong? This test, this BTSV, was proposed basically a couple of years ago to replace the conventional characterization binder which is used in Germany based on penetration and ring and ball, so on softening point. And this is basically the first version of the test, so the first cover page, which is basically can be translated introduction for the determining the deformation behavior of bitumen and bituminous binder with the dynamic shear rheometer, BTSV, procedure, binder fast characterization test. This test is based on dynamic shear rheometer and is, in this case, used to determine the amount of rejuvenator to target a specific rheological property of the blend of new binder, age binder, and rejuvenator. Is performed with an increasing temperature with a rate of 1.2 Celsius per minute, 500 Pascal, and a single testing frequency. And from this test, what we obtain is a temperature, TBTSV, and a complex and a phase angle at a specific complex modulus value of 15 kilopascal. At first, we have a plane which is giving us the temperature and the G star, from which we obtain the corresponding, as I said, the corresponding temperature based on the G star limit of 15 kilopascal and the corresponding phase angle. And based on that, we get what we call the BTSV plane, which is obtained by plotting the temperature of BTSV versus the phase angle. What we found is that when we move, when we blend binders, we move along this line that is targeting the final binder box, which may be different depending on the binder that we are using. But when we use rejuvenator, we are moving along a horizontal line. What we did in this study was to select a specific wrap binder, a specific wrap source, and we blended with 3 different rejuvenators, basically one soft binder and 2 type of rejuvenators at different percentage, 20 and 40%. And we target a final blend value of 57 Celsius for the softening point, and in this case for the bitumen type 0 Schnell-Verfahren temperature, or BTSV. After that, after we determine the amount of rejuvenator, we basically run simple conventional test on asphalt mixture to determine the resistance to permanent deformation, finding that the method was giving us actually a decrease in the increasing rate of permanent deformation, except for one specific rejuvenator. In the case of rejuvenator and not on soft binder, we had a decrease in the stiffness modulus, which can be also seen in the trend of the, or at least somehow seen in the trend of the master curves, with a softening at lower temperature, a moderate stiffening at a higher temperature. This is for 40% of wrap, while the first one, the previous one, was 20%. Then we look at fatigue, and we determine that the contribution of the rejuvenator to the mixture prepared with 20% of wrap was not so significant, although there was an improvement in terms of fatigue life, while this was much more significant at 40% of wrap. And what I care the most is to show what happened at low temperatures, which is much more interesting and very questionable. We ran TSRST test, so thermal stress restraint specimen test. And what we found out is that there is not consistency in the result. Because what happens is that we have an increase in the failure temperature of the mixture, although the failure stress basically, or strength remain basically the same. which poses some question on the method that we were proposing, so on the bitumen typisierung Schnellverfahren, so the BTSV, on the ability of really providing the correct amount of rejuvenator that is needed to rejuvenate the binder and the wrap binder in the mixture. Summarizing, what we have done was to try and evaluate the possibility of using this new BTSV method, this new characterization method, to design mixture containing reclaimed asphalt pavement and rejuvenators. While for stiffness and fatigue, we have a reasonable result. At low temperature, as I said, the results are relatively similar in terms of strength, but in terms of failure temperature, we are actually poorer performance. For this result that I presented, I just want to acknowledge the laboratory team of the Institute for Straßenwelt of the Pavement Engineering Center at Braunschweig, but especially I want to acknowledge Dr. Alex Weiter and Dr. Stefan Buchler. They actually did this work. And I want also to exploit this possibility to advertise the symposium that we will have in Braunschweig in September 17 and 18 on the chemical characterization bituminous material. It's a RILEM symposium. And on September 19 and 20, we also host the cluster meeting, the annual cluster meeting. Thank you very much.
Name of file is this one, yes. Finally, we got it. So I will try to summarize the outcome of one of the RILEM TG dedicated to asphalt hot recycling. So I can summarize the work of the TG as an attempt to answer three questions. The first question is more or less, can we put a number on aging? The second question is more or less, can we find a relationship between this number on aging and the rheological property of bituminous binder? And the third question is a little bit different. Is can we establish a link between the structure of the binder and the property, his mechanical property? So here I just put a typical recycling cycle. So just to show that here for a new mixed property we have the input which are controlled, and when we go to recycling, we have got an aging which is not controlled, so we need to check the property. Maybe it will work. Yeah. So we have to improve or to facilitate the characterization of the wrap before entering the new process. So to answer this question, we take the opportunity of other former RILEM TG, which build a database with binder property of the mixed, of a binder at a different aging step. You know, they started with a mix, two type of mix, two type of mixing, one lab and one plant, and they apply to this mix an aging procedure. So in order to have a ranking of an increasing wrap aging. So these are the different steps of aging, and at each step we've got the basic property, penetration, the softening point, and the modulus, and the carbonyl index, the FTR spectrum. So that's the candidate for the characterization of aging. So we'll go in detail for the FTR spectra. So the basic principle is that during aging, some oxidative groups, some functional groups are formed, and mainly carbonyl bonds and sulfoxide bonds. So they can be identified in the infrared spectrum. So in fact, if you conduct a RE beam in a thin slide of binder, some frequency or some array will be absorbed. So you can see that in this graph. So here you have an edge new binder here in blue, and here on the red line is an edge binder. So you can see here this example of the carbonyl. You have some more absorption in this for this wave number. So the problem is that in each lab, the method for calculation of an index from this spectrum are very diverse. So here I put an example of the area method. In fact, the principle is to define this area of the carbonyl and to compare it to a reference area supposed not to be affected by aging. So if you make the ratio of this area to this area, you have an index of aging. So all the labs use the same principle, but in fact, all of them have some different way of calculation. Maybe they change the bound, they change the reference, the baseline. So in fact, the results to obtain are very different. We start from the same spectrum database, and if the different lab use their method for calculating an index on this same database, you obtain very different results. So obviously we can put a number on aging, but an harmonization is needed to have the same aging index. But you can see that the trends are the same. So in the same, if you use the same method, the method of the lab, you have the same trends for the according to the aging. So the second question is, can we make a relation between this index and the property, the mechanical property of the binder? So as I show you, we have a database of G-star value. So it means a lot of data points. You see, you have for G-star we have a measure at low temperature and high frequency, to measure at high temperature and low frequency. So it was not possible to try to make correlation between all these value and the aging index. So the choice was made to reduce the data, all this 150 experimental value, to 6 parameters using a wet modified model. So mainly the model here, the parameters are here. If you are at a very high frequency and low temperature, you have only the spring, so you have a real value here. And if you are at hot temperature and very low frequency, you have the damper here, and you are here. And you have some parabolic element that control the tangent here to the shape, to mimic the shape of the modulus. So basically, we reduce all the experimental value to 6 parameters. So if we compare if you see the trends with aging, so we see that in each lab we see the same trend. In all labs we see the same trend. So G infinite here stay constant, and K, this slope here, stay almost constant. But the 4 parameters that are changing is this H here, this slope here, this balance here between the 2 parabolic elements, and a little bit the damper here, and the most significant one is tau. It means the way you are moving here on this curvilinear axis. So it means we have only, with aging, more or less we can say we only have 4 parameters which are moving. So we try to correlate to see, as we have some trends with aging index and some trend with parameters, these 4 parameters. So obviously we made we tried to see if there are empirical correlation and between the two. So that's what we find. So we find some empirical correlation between the carbonyl index in this case and this parameter. So one possible way to use that to help to characterize ripe is to find a special point for the binder. For example, here for the initial binder, you get the characterization of all the parameters for these binders, and then knowing the slopes you obtain during the aging process, you can predict or more or less have an idea of the property of your binder at different aging steps. So that's what we've got, but there's of course some lot of limitation. We have only have this correlation only empirical. There's not based on a scientific explanation. It was made only on 1 bitumen and on fresh bitumen. As Martin said before, the oxidation would be different if the binder is regenerated. And one of the limitations also we have seen there is a lot of aging calculation methods, so we need harmonization. An initial characterization is required, and is the aging method representative of aging insight? And finally, is it transposable to insight aging? That's the question. But it's a track that could be explored to help to characterize RAP, a fast characterization of RAP. So the third question was, is it possible to have a relationship between the property of the binder and the bitumen structure? So it's based on an assumption called the delta method, which the assumption is that the phase angle of G star reflects relaxation of the molecular structure according to their mass. So basically, if you take here a phase angle curve, the basic idea is when the angle is 0, you have an elastic behavior. So no structure, you assume that no structure are relaxed. And when the angle is 90 degrees, you assume that you have a viscous behavior. So you assume that all structures are relaxed. And as you lower the frequency, the molecular weight, the molecule relax according to the of ascending mass. So more or less, you can see the phase angle like a grading curve, maybe grading curve of the molecule of the binder. So it means that in fact it's a change in axis. The x-axis came from phase 0 to 90 to a cumulative distribution, to 0 to 100, and this axis starts from a frequency axis to an apparent molecular weight. So mainly, if you go right with the frequency, it means that your molecular weight is lower. If you go left, it means it's higher. If the the change here is very steep. So it means that you have a very concentrated range of molecular weight. If the change is slow, it means that you have a large span of molecular weight. So that was the basic assumption, and the idea was to test it on the database of the RILEM. So that's what we find. We find that here it's the distribution, if you have the molecular weight assumed by the method, and here the fraction. So here you have the virgin binder here with a peak in a low molecular weight, and as you age, you have a peak which grows on the high molecular weight. So maybe an interpretation is that we are decreasing the low molecular weight population and increasing the high population weight during aging. So that's what we find, and maybe it could be of some help to characterize rejuvenation and or bitumen aging. So the potential perspective for this method is for recycling, of course, structural characterization, but mainly I would say can be used as a rejuvenator assessment to improve mixing law. More or less, there's something in that Martin presentation that are rather similar from that. The strong limitation is that the validity of the assumption. So that's the question. So to sum up, the FTR could be a promising method for RAB characterization, but we have to harmonize the calculation method and also the measurement process, because there are different kind of procedure for measurement that have an effect on the result. As to the link between the aging index and the rheological property, it seems that it's reasonably predictable for fresh bitumen, but this also should be investigated a little bit more. And as to the delta method, it could be a promising tool for to a better assessment of the aging and to understand what is going on at the structural level. But still, it needs to be verified and checked. So these are some explorating tracks, and now the idea is to see how they can be used in real life and if they can be of help in recycling at the industrial level. So thanks for your attention.
Thank you. The last presentation on hot and warm recycling is by Dr. David Lopresti. Dr. Lopresti is a principal research fellow of the Nottingham Transportation Engineering Centre at the University of Nottingham, and his expertise is sustainable engineering. Dr. Lopresti's research is both applied and fundamental and involves investigation of effective techniques for recycling waste, secondary materials into civil engineering applications such as roads, railways, and roofing membranes. Also, with the goal of investigation sustainable asset management for preserving existing infrastructures as well as envisioning the future ones. Dr. Lopresti is specializing in smart technologies, life cycle management, and multi-criteria decision making. Please welcome Dr. Lopresti.
Perfect. Well, hello everyone. Good morning. Let me tell you first of all that I'm very happy to be here because it's Brazil, place where I come always with pleasure, and because I can see whole Brazilian friends and hopefully new Brazilian friends from today, but also we can share with the colleague friends of the TC RAP that are led by Gabriele and Ishan. Thanks for your efforts. But let me tell you that I'm really happy to be here now because I come from 24 hours trip with a lost luggage. And at the end of this trip, I had some angels in form of 2 Brazilian women that even attend me to got me dressed. And for this, I apologize if I don't have a jacket, but I hope you understand. So, I am Davide, and I work in the Nottingham Transportation Engineering Center, which is a research center that historically looks at fundamental research in materials for transport infrastructure. But in the last 10 years, we kind of shifted the trend and also went towards applied research for existing infrastructure, but also for the future system that will come. We have different enabling activities, but the one that I really would like to stress today is the sustainability. And the way we tend and we try to introduce sustainability in this world is through collaborative projects. We think that such a complex challenge needs collaborations. And in the last, I would say, 10 years, this is the old presentation, by the way, but it's okay. And I'll go on with this one. During the last 10 years, we actually have been involved in several efforts, and these are mainly related to hot mix asphalt or warm mix asphalt for wearing courses. Recently, we also trying to understand how to incorporate biobinders with some friends that are also here in the audience. Lauren is one of those. But how do we do that? Well, what we know to do is doing research with our materials, trying to understand how to make design, testing, and also field experience. But our main research question in these years was, it is actually maximizing recycling something that we can call sustainable. How can we assess it? How can we assess whether we are actually also minimizing the impact? So the other, is it here? Is it here? All right. Sorry. The other stream of research that we undertook was trying to understand how to do sustainability assessment and trying to actually understand that we're actually minimizing the impact. So today, I'm going to show you some results of one of the projects and are related to maximizing recycling in wearing courses. This was an effort that finished some couple of years ago, 2-3 years ago, and was financed by the Conference of European Road Director, as the aim was really to understand, absolutely blue sky thinking, understand how we can arrive to 100% recycling. What we need to do, what are the challenges, what are the mistakes that we should make. This project was led from a university in Germany, and I thank all the people that work in this project. And there were university involved as well as industry and association that help get data as well as expertise to actually undertake the project. So the project was divided in different stages, but we look at understanding how to increase recycled content by looking at mixed design, also the blend design that we will see later, but then also playing the asphalt plants, and at the end understand the performance and the sustainability of the technology we developed. So, going very quickly, and again, this is the other presentation, but it's okay. What we did was trying to understand, first of all, how to characterize the wrap. Because wrap is such a complex material that we can't just use the methodology we know. We need to understand how to characterize this material. And this is exactly what the TC wrap is trying to do. Then we also look how the grading curve that we can consider for this new mix design. Because again, we know how to work with white aggregate and a binder, but what happens when we have wrap? And then we made an effort to understand how to make a preliminary, what we call binder blend design, to consider the interaction between new additives binder with the old binder in the wrap. We did this for 2 case studies. One was an SMA from Germany, and one was an asphalt concrete from Italy. And we tried to understand how to arrive to 100% of recycling. So how can we actually assess what's the maximum amount? Well, we consider 2 paths. First of all, we look at the aggregate and try to understand whether there is some limitation. So usually, when you do a mixed design, but am I changing with this, or it's you? Ah, it's you, okay. Good to know. It's me? Okay, thanks. You say yes, no? Right, so usually, currently, when we do a mixed design, consider a grading curve of wrap, we consider the wide curve. So we get rid of the binder and we consider the stones that are the product of the extraction of the binder, right? So if we, in case of the German mix, with that wide curve, we could arrive to maximum 70% to stay within the bands. So we say, okay, let's go on with this one and let's try to understand, to make some mixes with the 70%. But with the Italian one, we say, okay, why won't we try something a little bit more challenging? So we used the 30, the 60, and everything was fine. But then we went over and there was some problems. So we thought, well, but maybe, you know, as in life, nothing is very much just white and black, right? Maybe there is something in the middle. So if the white curve is the curve of aggregates without binder, and the black curve is actually the one with binder, we say, what about if we consider something in the middle and something gray? So we consider to include in the mixed design the partial blending concept. That is, I mean, we didn't really know how to assess it, but at least we tried to consider in the mixed design procedure. So what we did was to attempt and make an hypothesis that there could be possibly an activation of 60% rather than 80% of binder. What does this mean? We are trying to understand as well in some effort that I'll present later. But the point here is that we mathematically derived some curve. So again, this is just an assumption. But this would allow us to include the partial blending concept in the mixed design. And with this, we even arrived to produce 90% wrap that I don't present today, but there are the deliverables, and I can guarantee you that they kind of worked. Now, you need a plan to do that, as you were saying, and we went in Germany for this, because we didn't find in Italy. So this was one of the limitations. So the grading curve and the current way of doing mixed design possibly can be improved. The other way was trying to understand what happens with the bitumen path. So, now bear with me just a second. This is a concept that we try to include to improve what we call blending charts. So, if the orange one is the binder of this new mix with a loader wrap, you would agree with me that the main part of this binder will be the binder from the wrap itself. That is the red one. Then, if we put some recycling agents, then they can be additive, lubricant, warm mix additive, depending what you want from the new binder. We can consider the replaced virgin binder as the contribution of this old binder from the wrap to this new binder in the new mix. So if we consider this concept, well, of course it will vary based on the binder content of the wrap, as well to the concept of the partial blending. So what is the amount of the activation of this binder from the wrap? So what we did was to go in the mix design by having some input that not only were varying the amount of RAP, but actually were making an attempt to vary the activation, just making a hypothesis. And then, based on the activation, you actually have different percentage of replaced virgin binder. These allow us to actually build some new blending charts. They usually have RAP in the x-axis, but in this case you will have replaced virgin binder. And thanks to this, we could basically see what happened when you changed the amount of activation as well as the amount of RAP by considering the replaced virgin binder quantity. I'm not staying too long on this because I know that it's quite technical, but happy to answer any questions. And what this thing allowed us to do was to actually check, doing some quality control on the binder that we selected as a new virgin binder, or the type of rejuvenator, or the type of dosage, because thanks to the blending chart, we could see which were the property that we wanted to obtain. So another limitation, in this case just for the binder, were the target that you want to achieve. But considering the replaced virgin binder, you can also consider the partial blending concept in the blend design. Again, I hope that I was clear, but for more details, there are some publications that we actually had in this topic. Right, so we then go on, went to the plant. We actually made this, but there are some deliverables that you can find. I didn't publish a lot of these things. I need to publish actually, but I have no time. And then we actually went for the performance assessment. And just as a takeaway message for you, for this part, if you want to maximize recycling in the wearing courses, it is fundamental that we find a way to actually characterize better this RAP. Because wearing course is the functional course where we have to guarantee not only performance, but for instance skid resistance, the mix design by using hot mix or warm mix methodology needs some innovation. And the grading curve or the RAP is a limitation, but the partial blending concept can actually help. And on the other hand, working preliminarily on the binder blend and understanding, making a quality control of the different rejuvenator or additive, the dosage, and comparing them with the target that we have for our final blend, I think this needs to be included in any work that will go forward in this direction. So, this is the first part, the technical part, right? How do we maximize recycling in the wearing course? And that's a little bit of contribution that we try to make. But the other part, it's about, just let me see that one thing that is needed is understanding this, how we can actually assess the degree of activation. And this is an effort that we are doing within the TC RAP with Camilla. And we just started, really. So I think in the next 2-3 years, we hopefully will also provide this type of contribution. For any information, we have a page on ResearchGate. Oh, you know Camilla is here. Now, how do we actually minimize the impact? So our effort was not only directed to understand technically how to do it, but we wanted to understand how we can actually consider this choice sustainable. So what we did, I'll try to go very quick here, but we contacted different road authority and tried to make a comparison that could be representative for Europe. So we get different data, we built some case studies, and we did an impact assessment. It was both environmental and economical. But today, I'm just going to talk about the environmental one. So the idea was to consider an operation. There is an inlay. So basically, you take away the layer, the wearing course, and then you put a new one. That is an operation that we do constantly. And we're going from the product stage up to the end of life. Not consider the use part, because it was a comparative analysis, and it's quite complex, to be honest. So the idea was to make a carbon footprinting. I don't know if any of you have never done this type of exercise, but basically we want to account at least for one environmental parameter. In this case, it was the CO2. We used some free tools, and we got all the information from the asphalt plant. We knew the mix design recipes, and we consider also some realistic maintenance scenario of this wearing course on 3 different countries. Now, as a main hypothesis, we consider that the durability of the current procedure, the current mixes, so the one without wrap, was actually the same of the one with wrap. Okay? This is a massive hypothesis, massive assumption, but this will at least allow us to go on and get some information. But durability is something that we need to assess better. So, going very quickly, we built some case studies, so getting a site where there were actually this inlay procedure, as well as having transport distances from the asphalt plant. This is where I come from, by the way. I come from Sicily. And we get more information on the site, as well as having details about the procedure to actually make this maintenance operation. And one of the important things is actually to assess also the different transport distances that we'll see they are key in this type of assessment. So at the end, very briefly, and just about carbon footprinting, we saw that to make an inlay operation of wearing course with, it was hot and warm technology with different amount of wrap, we found out that in terms of CO2, we could say that it is very subjective, as you can see, but generally you can say that increasing the amount of wrap could lower the CO2 or having similar results. But again, responding in absolute terms is very difficult. It's case by case. Just to give a little bit more insight on this. What is this one? I think there is a graph, but you can't see the bars. Right. There was some colors. Anyway, this is the carbon footprinting of the whole life cycle. And I can guarantee you from the colors that what we call hotspot, so the part where actually you can see the highest amount of emission, in this case was at the asphalt plant, cradle to gate. But also the transport distances, in the Italian case studies at least, was a big contributor to the emission. When we moved to the German one, I'll go directly to the German one, we saw that the asphalt plant had a big role, but the transport had a much more marginal role, right? While when we went to actually understand just in the asphalt plant what happened, we saw that in that case, the transport distances had actually a bigger role, as well as the emission coming from heating and mixing. So, results are in this deliverable, but what I want possibly to give as a takeaway message is that if we consider durability the same as we did here, well, in that case, you can say that increasing the amount of wrap actually provides similar or lower carbon emission. But if the durability, for instance, is lower, it's a completely different story. So we have to be careful when we try to maximize recycling and saying there is an environmental friendly option. Another takeaway message is that it's very much case by case. You need to do what we call hotspot analysis. And for instance, we found out that if we have transport distances for building the road or maintaining the road, they go over 100 kilometers in all the case studies, recycling almost didn't matter. So the impact of transport in terms of CO2 was bigger than any possible way of recycling. Just to go away, I think that from this study and from what we are trying to do, I think that the main effort and hopefully the main message that can go across to you is that in order to make sustainable pavement, to really introduce sustainability, we do have to continue what we're doing our pavement design, working on materials, but alongside we need to have a sustainability assessment exercise that is representative for each country, where we can actually have a loop and understand that what we are doing is actually sustainable. And once we have an option, an alternative, the different alternative needs to be accompanied from best practices, saying, for instance, we need to reduce transport in this case, we can increase recycling in the other case. It's very difficult to talk about in absolute term, but it has to be specific and case by case. But it needs to happen. Otherwise, it will be very, very difficult to say that what we're doing is sustainable in general. Well, having said that, I just want to say that we are continuing in this direction. We actually just been awarded a project for the next 2 years for the Conference of European Road Director that will build some guidelines that will be used in Europe for sustainability assessment, but can be actually spread also somewhere else, and maybe in Brazil. So thank you very much. These are my contacts, and for any question, please feel free to ask.
Now we're moving to the next topic, cold recycling. First presentation is performance of cold recycled pavement, North American, European, and South African research and case studies. This presentation will be presented by Dr. Alan Carter and Dr. Kim Jenkins. Dr. Kim Jenkins is a South African civil engineer. He focuses on research into cold recycling technology and sustainable materials and practices, such as bitumen stabilization with either foamed bitumen or emulsion. Kim is currently in the research chair in pavement engineering at Stellenbosch University, sponsored by the South African National Roads Agency. Dr. Alan Carter is a full professor in the construction engineering department at École de Tecnologia Supérieure ETS in Montreal, Canada. Most of Alan's research work is on bituminous materials characterization, on cold recycled materials, and on pavement design. He is a past president of the Canadian Technical Asphalt Association, CTAA, a director at large for the International Society of Asphalt Pavement, ISAP, and the secretary for RILEM Technical Committee on Multi-Phase Characterization of Cold Bitumen Emulsion Materials, CBE, and of the TG1 on cold recycling of the TC on asphalt pavement recycling. Please welcome Dr. Alan Carter. Sorry, I forgot someone. Dr. Gabriele Tebaldo will also present in this section. Dr. Tebaldo is Associate Professor at University of Parma and Joint Professor at the University of Florida. Dr. Tebaldo's research interests focus on mechanical performances and cracking behavior of bituminous materials, cold and hot recycling of RAP, and design of multifunctional and resilient asphalt pavements. He is the first past president of ISAP, the international representative in the board of directors of AAPT, Association of Asphalt Pavement Technologists, chair of the RILEM Technical Committee on Asphalt Pavement Recycling, secretary of ISAP TC on Asphalt Pavements and Environment, associate editor of the international scientific journals Road Materials and Pavement Design and Materials and Structures. We'll begin with Dr. Alan Carter.
Okay, so good morning, everybody. Happy to be here. We're kind of short on time, so I'll try to make this quick. Okay, so we do cold recycling in North America, and Canada, and United States. I would say kind of a lot. Okay, it's only the recycling of the asphalt layer or the asphalt plus the base layer. And there's a lot of that going on. But even if there's a lot of job site, there's a lot of really, in Quebec, for example, the French-Canadian part, we've been doing cold recycling for 20, 30 years now on high-traffic roads. The main airport in Montreal Airport, the base layer, is cold recycling. Okay? It's doing very well. Okay? But in lab, not so much. So we have problem to actually make the link between the performance in the field and the performance in the lab. Okay? So I'm going to concentrate on the lab part. Just to be sure that we all talk about the same thing. Okay? So cold bituminous material can be named, can be characterized depending on many things. In this case, we do give name according to the amount of cement, if any is put, and the amount of bitumen. The amount of bitumen can be in the form of foamed asphalt or in the form of asphalt emulsion. We're not talking about the amount of foam or the foam emulsion, but the residual binder that's left when we're done with the water is out. So usually we're in that area. Okay? So cement, bitumen treated material or bitumen stabilized material or cold mix asphalt. Okay? So we're in that area. The amount of cement that is kind of the maximum before we get to, I would say, like a fragile concrete behavior, it depends. There's no agreement on the exact number, but it seems above like 1.5 to 2.5%, you're in the cement-like behavior more than bituminous behavior. So why do we have problems with those materials? First thing is an evolutive behavior. That means that when you put it down, in the first hour, it has a given modulus, a given reaction, a given cohesion. An hour after that, it's something else. But 30 years after that, it's also something else. Okay? So it does evolve with time, which makes it complicated to actually analyze, characterize. There's no agreement on mixed design procedure. And I'm not saying no agreement only in one country. Okay? Within a single country, there's no agreement. And within each country, there's no agreement. Okay? So we don't know exactly what is the best technology, what is the best method to use. No agreement on the cure. It's a specimen that have an evolutive behavior like I mentioned, and if we don't agree what the cure should be, we have different results. No agreement on how to make lab specimen to represent field. No agreement on which mechanical properties should we look for, and from which test. So, whoa. Won't be long. Maybe not. There you go. Stay there. Good. Okay. For example, I'll just show you for the cure. Okay. I can show you those kind of table for many other things, but for the cure, those are all different. Every line is a different cure. That's all supposed to represent basically the same thing. And you'll have lab results that show actually that it does work. So in a specific case, that much time at that much temperature, that much relative humidity, ended up giving the same as a year in the field. And then you change the field place. So instead of having a nice, but it's supposed to be nice and hot and warm in Sao Paulo, but we didn't see that in the last 2 days. But let's say that in some Montreal weather, very cold and windy and everything, it's not the same field, performance. And so in the lab, we should not do the exact same thing. So in order to look at that, there was a TC group that we're all part of, so the TC wrap. And the TC wrap is separated in different TG. Maybe. One more. There you go. So I'm co-chairing basically the TG1 on cold recycling. The other one are not that important right now, okay? Because we're talking only on cold recycling. Really having a hard time with this. So the objective behind TG1, Am I doing it or you're doing it? Okay, maybe, almost. Can you go back up one? Thank you. So first, evaluate the ability of a fragmentation test to actually characterize the wrap itself. I'll come back to that in a second, but right now we don't have any way to say if the wrap, the recycled asphalt pavement that we put in it, is it good or bad? Will it work? Yes or no? Except doing like a full gradation and extraction of the bitumen and everything, not necessarily useful. Thank you. To quantify the impact of the compaction type. So there's many different method, equipment to compact the material. So we need to verify that. Evaluate the effect of the type of binder. As I said, the bitumen can be put as foam or as emulsion. In many places, Quebec, for example, and in all other provinces in Canada, it's considered equivalent. So you put one or the other, it's the same. Put the cheapest one. Okay? And in our case, often foam wins because it becomes cheaper than emulsion. And to implement a volumetric approach, so to do with cold recycling a bit like the same approach that is used in hot mix. So the fragmentation test, if you've done fragmentation on aggregate, it's basically the same thing. Okay? So we take the wrap, we try to crush it, and we look at fine before and after. The reason behind that, the rationale behind that, that's part of TG, I would say, 6 of TC SIB from a previous RILEM committee. It was the fact that when you compact cold recycled material, does the gradation of the wrap itself change during compaction, during laydown? If it does change, so the properties that you measured in the lab are not the one that you're going to find in the field if there was a change in there. So this test is supposed to say, okay, if it breaks apart, we'll call it bad wrap. If it doesn't break apart, it will be good wrap. Okay? So that's a test to characterize this. So to do this, we have 12 participating labs separated basically all over the world. We have 2 sources of wrap. So like basically 3 tons, a bit more of wrap to play with this. Those are the lab that participate in this. So there's a bunch in Italy, so United States, Belgium, United States again. So you see there's a bit of everything. And of course, Sao Paulo is there. Okay? Of course. Okay? Even if it's complicated to get bitumen here, but that's another story. So yes, because for that exchange program, for that research program, we're all using the same wrap, the same bitumen, the same cement, and the same filler that we put in it. So it means that yes, we have to ship that material all around. Shipping everything is not so complicated except for the emulsion. The emulsion is tricky, okay? And I will take the opportunity to mention it. Ninas is actually producing and giving us the emulsion and the bitumen for that, so that's a big deal. The 2 wrap that we use, the good and the bad wrap. So basically, this one is the good wrap, the wrap 1, at 4.6% bitumen in it, and 5.5 for the other one. This is, give or take, a 0.14 or even 0.16 millimeter wrap, and it's a 0.10 for the bad wrap, if you want, okay? So that one comes from Italy, that one comes from the United States. So what we're looking at is 2 things. So different compaction and then different tests. We chose a given cure. So we're going to do 14 days at 40 degrees Celsius, and this is supposed to represent easy to get relative humidity. Right? Those numbers were chosen to be representative and to be easy to be done by every lab. Okay? As for compaction method, as I mentioned earlier, we have different compaction methods that are used everywhere. And those, so gyratory compactor, Marshall, Duria, it's something from France. Vibrating hammer, Proctor, slab in the case of some of the labs. So with all the same material, everybody will try to compact the material with whatever equipment they have. And the goal is to get the same air voids level. Right? We're aware that nobody will get, let's say that we point for 9.8% air voids, nobody will be at 9.8 precisely. Okay? That's not possible. Okay? But we should be around that. Once we compacted the material, we do a bunch of tests. Which tests you do depends what you have in your lab. So we go from indirect tension to wave propagation to complex modulus to everything. Okay? The goal is to try to see the influence, again, of different wrap, of different compaction. And this will be done, the same thing, exactly same program, done with foam on one part and done with emulsion on the other part. So we compare also the type of binder that we have in it. So just to give you a quick overlook of the initial results that we have. So if you look at the curve, let's see, okay, the two bottom one, so the square and the circle. So the square is the top one, the circle is the bottom one. So to see the compaction of those mixes. So those are two 0-10 wrap. It's a basically adjusted wrap 2 to be a 0-10. And since it's different wrap, they have completely different behavior, compaction behavior, which is normal. Okay? And it's not a problem. That's what it is. If we want to have the exact same behavior, we should change the gradation so they have exactly the same gradation, which is not the case. And as I mentioned earlier, what we need to shoot for is a given air voids. So for that, if we look at, those are Marshall numbers, those are Proctor, and those are gyratory compactor, okay? It's a weird graph because I would need like 3 more scales on this, okay? But the point is that it's possible to reach the similar air void level for all those compaction methods. But to do that, we'll have to change the number of gyration, the number of hit on the Marshall, everything, okay? So we choose one and we go from there and we try to compact. Last result that I can show you, this is with foam. So with foam we use a third set of wrap just to be sure that we have something that we're not using the precious wrap that we need for the exchange program. So it's compacted with Marshall, with a 100 millimeter mold. And then we have gyratory 100 and 150. So they were compacted to around 9% air void, so it ended up at 10% for 150. Something I did ask for the result. For the gyration, to get that level, basically for that wrap, we're at, I think, 15 gyration. So basically, we just put it in and plop, we stop. Okay? And it did work. And then we look at ITS. So a few things that we can see. First, those are statistically different. Okay? So the impact of the compaction method is important. Okay? So that's one thing. Second, if we look at gyratory compactor, the size effect is also important. Okay? So if, for example, if your minimum value that you need to reach for a contract perspective, it's 500, and if you have a 6-inch or 150 millimeter mold, it doesn't work. It's the same material. You did the same mix design. It will behave the same way in the field. But in the lab, it works, doesn't work. Okay? So that's an important point. So that's why we do all this. So I hope that was quick enough. I'll try to, yeah? Did I do good on time? I'm pretty sure. Okay? I'm done.
I'm going to move forward in another aspect of the problem related with laboratory performance and field performance. Basically, the question is how it's possible to properly characterize the bitumen stabilizing material. First, let's define clearly what we have. The material that we are talking about is bitumen stabilizing material, so something that is in the middle between an unbounded material and a fully bounded material. So we have, just to be clear, an amount of bitumen that is almost half of the bitumen that we have in a fully bounded asphalt mixture. That can be hot or can be cold, but the difference is the amount. So what's happened in the material? We need another important component that is the active filler. And if we check in the Sabita guideline for bitumen stabilized material, we have that the maximum amount of cement is 1%. Why that? We don't need the cement to bind the material, but we need the cement, as all the other active filler, to carry the bitumen. So what we are looking for is the air voids. So we are using cement or hydrated lime, that is even better, because they have a higher amount of void respected with the traditional filler. And we need that, And if we look also in the surface of the fine part, of the filler particle in comparison with the coarse part of the material, we can clearly see that the surface in the filler, let's say in the filler component, is much bigger than the surface that we have in the coarse side. Almost 200 times bigger in terms of square meter per kilogram of material. And so why we need these? We need these because can you click on the video? Okay, this is the foam bitumen that is generated in the foaming chamber, and this is what's happened in the mixing part. So we have that the blasting generates a small drop of bitumen that are caught by the filler particles. So you know now why it's important to have a high void element that can catch the bitumen. And after that, each particle of filler with the bitumen is this inside of the blend and help the blend and the mixer to be binded. But we are talking about a non-continuously bounded material. So we have some spot with bitumen that bind the mixer. And we can clearly see here in this microscopic picture, you can clearly see that we have part of the aggregate that are not covered by the bitumen and part where we have the bitumen. And you can clearly see that if you keep in your hand, you have this spot in the hand that you will see that is a completely different story when we have the emulsion. In this case, when we have the emulsion, we put the material together with the water, and again is the filler that caught the biggest part of the bitumen and move the bitumen inside of the mixture. So in the first case are the blasting and the filler that are the carrier of the bitumen. In this case is the mixture that is the water that is a carrier of the bitumen inside of the mixture. But again, considering the different amount of the different surface of the filler, the biggest part of the bitumen goes in the filler. So what we have is again a continuously bounded, a continuously covered material, but we have to remember the amount of bitumen that we have in the mixture. When we have a fully bounded material with 5%, 4% of material, all the aggregates are fully covered in the same way. But if we look at the effective asphalt film and the effective asphalt thickness, when we have only 2% of bitumen in the whole mixture, we cannot have the same thickness of bitumen on the aggregate that we have in the emulsion. And this thickness doesn't allow this to have a fully bounded material. Even if the aggregates are fully covered, the effective film thickness is so thin that cannot guarantee a fully bounded material. So in another way, we are in another not completely bounded mixture. So, and if we look here, we clearly see that everything is covered, but the different level of black clearly show that we are not in front of a aggregate covered with enough material to completely bind the aggregates together. But the difference is clear. Here, if you see, this is Professor Jenkins' hand. The previous one was my hand. And you can see that this is that we have a fully painting that is show that the material is fully covered, but as you can see here, with a very, very thin film of bitumen. So we are in a different way, but more or less in this condition, with an half-bounded material that is generally located below the wearing course or the surface course of the material. So the point is, how can we characterize this kind of material? Because we are, if you remember the graph, we are not in the, let's say, in the field of the hot mix asphalt and the fully bounded mixture. So we cannot approach this material, as Alan showed in terms of the compaction, we cannot approach this material in the same way that we approach the hot mix asphalt. So we need to identify something that allows us to catch all the property, and particularly the two phases of the material, that is the half-bounded phase and the granular part, with the friction and the interlocking of the material. So one proposal to characterize that was a simplified triaxial test method. Why the triaxial? Because the triaxial allow us to catch the cohesion, but also the failure envelope and the friction angle. So we may have all the mechanical parameters that can give us the full picture of this material. And to do that, this is a prototype developed by Viergen. It's a simplified mold with a air pressure chamber that can give us the confinement and the vertical load. So this method allows us to show how the performance are different from and how much the performance are different from an unbounded material. Generally speaking, if you will check the failure envelope of a bitumen stabilized material, you will have something like that with a higher level of cohesion in comparison with an unbounded material. And these are some preliminary results of a research project that is going on in my lab. And my student did a series of specimens, same size distribution, same amount of bitumen, but different amount of active fillers. 0 in this case, 1.5 of cement, 1%, 1.5, and 2%. And these are after 28 of curing, just to be sure that all the setting reaction of the cement were done. And you can see here, the indirect and size strength are not so different for the other material. Basically because there is a big influence in the size distribution. But if you go here and you look in the cohesion, you can see a very big jump in the characteristic from the 1% cement and 1.5 and 2%. Something that was not possible to identify with the indirect tension test. And if we move also in the failure envelope again, you can see a strong difference among the three different of amount of filler. So this is the point. So to evaluate the real strength, you need to have the proper tool. So what you say? Force Brazil? And now Kim, I think that can go.
Good morning, ladies and gentlemen. For me, it's a great pleasure to be here. You would have seen from the three speakers in one project, we come from 3 different continents. So this is like herding cats to have the 3 of us speaking at the same time. I would like to focus a little bit, because of the RILEM TC related to RAP, also just to highlight a few more points about the research and the important aspects of the performance of this material, specifically with the influences of RAP. So picking up from some of the previous speakers, you will see that the guidelines now are considering the requirements for grading and the types of aggregates, differences whether they are virgin aggregates or RAP if you're using the cold recycling technology. And another thing I'd like to focus on too is how we manage variability, and we've heard it from previous speakers as well, is that with recycling and then even re-recycling, as Professor Camilla was telling us about in the one project, and Professor Liedi was also talking about very similar things, we need to be aware of these different aspects. So here are just a few findings, also linked to the RILEM group, as well as some of our research where we've had 4 PhDs and it's now 19 or 20 master's degrees specifically focused on this technology. You can see here, linking to what Professor Gabriello was saying, the importance of the filler as a carrier, but also to create the bond between the bitumen and the aggregate in the presence of water. And if you've got high percentages of RAP, you need less filler because the existing binder has an affinity for the new bitumen that you're adding, either foam or emulsion. What's very important with research is to also recognize the differences working with hot and warm technology as opposed to cold technology in terms of what gradings should we be targeting. And the way we obtain the samples for the projects where we're using the cold recycling technology, whether we do it in situ or in plant, we have different possibilities. And the way, very seldom if you're investigating a road and you want to apply this type of technology, will you be able to get a sample from these recycling machines, because you're just taking a fairly small sample and it's very expensive to get the machines on site. Often a milling machine will be used, and now we've got to look at the variables of the material that is going to influence its grading. These milling machines should, if you want a good grading, which is a nice continuous grading for cold recycling technology, should be operating at about 3 meters per minute. But as you can see on this chart over here, the sample that you get, and in fact what you will get in reality with recycling, is very much a function of the speed of advance of these machines. So we should be aiming for the higher line, the finer grading, it's continuous, which is done at slow but the correct milling speed. If you're going for production, as is often the case, you're going to get a coarser grading. And we need to consider these things in our research as well. If we look at other scenarios, getting samples from the road, it's usually more cost effective to use a small milling machine like this. If you use a small milling machine, it's often used in a very slow process that grinds the material, that then can break it down. This is now very different to the warm and the hot process, where it's more thermally related. The temperature will help distribute the original RAP mix into its components of aggregates. Not entirely giving you the original grading, but with cold recycling, remember the material is at ambient temperature, which could be 20 degrees, and then you've got lumps of the asphalt. But what we also don't want is too fine a grading where the milling or the sampling machine is actually crushing the aggregate. We just want to separate the aggregates for our research. On the other end of the scale, if you do your research on this good grading, the target grading that gives you the smooth, continuous gradation, if the actual project is dealing with a heavily crocodile cracked or alligator cracked, as Americans call it, road, then those blocks are very difficult to provide a smooth grading, because then you're going to get a coarser grading and you can result in that type of condition. And this is where the process of cold recycling must be linked to the research and the testing that we do. There are solutions, because if you're going for in-plant type of recycling, then you can take a coarse grading like that, you can process it through an impact crusher and process it to give you your target grading. Alternatively, there are also in situ recycling machines, in place recycling, that instead of milling the material upwards, which can give you slightly larger aggregate, it uses a down milling process which does more pulverize the material. So if in North America they use some of these machines, in both Canada and the United States, but I think there are 1 or 2 machines also in China. Not generally available, but when you're working with 100% wrap, we need to very carefully consider how the grading is controlled in the process. Professor Allen was telling us about the vibrating hammer as one of the components in this round robin. It's a process that came out of our research that's come from many years now, and the advantage of using the vibrating hammer is that it simulates both the frequency and the amplitude of compaction machines that are being processed in the field. So it'll be very interesting to see the results that are coming out of that research with different types of wrap. But the research up to now has shown a good control over variability, and I'll show that in a minute. So there's a little bit of repetition with what Professor Gabriella was telling us. This is a recommended type of approach to give you an idea of the number of repeat tests that are needed to give reliable results. So when you start doing triaxial tests to evaluate just one type of bitumen stabilized mix, you need to do, we recommend, at least 10 specimens. So you've got 8 specimens, 2 repeats at different confinement pressures for the triaxial, and 2 in the soak condition. And we even do an outlier test to first evaluate the compaction in those, to see that in each specimen, to see that it's not outside of a certain reliability limit. You've seen this already, so I'll just would like to highlight something of it, and that when one is doing the triaxial testing, you will soon see, and this is the benefit of having 8 tests, 2 repeats at 4 different confining pressures, in terms of the reliability of that result that you get. The reason being that the shear parameters, the cohesion and the friction angle, are not just a specification test tool, they're also parameters that links directly to the performance, and I will explain. So the one thing is we look at the reliability, and as you can see, with vibrating hammer compaction and good quality control, one can get very good correlation coefficients, and one should get that. Otherwise, you've got unreliable results. So some of the other benefits of using the triaxial to augment RTS type of testing with these cold recycling mixes is some of the technology development. For example, we've used CT scans. It's a fairly simple device, this that we see over there. But we've looked at the scans through the triaxial specimen, which is built in 5 layers of 60 millimeters each, to see that there's a good bond. And we look at it volumetrically from the CT scans. So step by step through the procedures, when we talk about vibrating hammer compaction, it's not just an open procedure. It's got to be a test method where all the variables that can make a difference need to be incorporated. Small things are important. With the other part of the research has been this wet to dry ratio of RTS testing, and how does it translate into triaxial wet to dry ratios. And what the results coming out of this, the research is telling us, is that the triaxial testing gives a more reliable insight into moisture damage than the RTS testing. But as a starter, looking at different types of mixes, you can handle more variables with RTS because the specimens are much smaller. They take up less material, less preparation time. But one ultimately does need a reliable test that can link to performance. Where the difference between RTS and triaxial has also shown differences, we heard about recycling and re-recycling mixes. Well, this is an example of what happens if the wrap is providing some unusual results. This came from a project where the wrap that was being used provided pretty good RTS results, but poor shear parameters from triaxial testing. And it was only through the triaxial testing that we recognized there was something strange about this wrap, and then we realized it was bitumen rubber asphalt that had been milled out, and it was some of that viscous sponginess of the behavior of the bitumen rubber binder that was influencing the result, and it had to be blended to find what is a maximum blending content of that specific type of wrap. There are always solutions, but you have to understand the input parameters. Okay, and then one can also look at temperatures when you're working in high temperature areas, because all of these tests, the RTS and the triaxial, are carried out at 25 degrees. But obviously it's a viscoelastic, thermally sensitive material, which we need to be aware of. So if you're working in really high temperature zones, and I've had the benefit, let's say, the privilege of working in some really high temperature areas where it can influence the deformation behavior, and there one can simulate that also with a triaxial. So you can elevate the testing in certain circumstances, the test temperature. So finally, just to round off with the last slide, or second to last slide, where this fits in, I mentioned earlier that the evaluation with triaxial testing isn't just a specification tool, it's also a link to structural design. And how we do this is we for mechanistic empirical type of design, one first looks at your principal stresses in your BSM layer, just analyzing the one layer and its performance. So those principal stresses based on the wheel loads and the layer thickness and the resilient modulus, as we know, we will get a stress distribution which we can relate to, for example, the Moore-Coulomb space. We also know for that material, if we've done triaxial testings, we've got some monotonic strength parameters, the cohesion and the friction angle. And then we can use just a deviator stress ratio approach, the ratio in diameter of the applied stress to the maximum stress, in other words, the shear strength of the material, what it can handle. And that deviator stress ratio relates to the rate of rutting, in other words, the slope of these permanent deformation curves with repeated loading. And this is, Professor Camillo mentioned it earlier, the approach that we have now developed and will be testing for different environments. It's already been tested for at least 25 different conditions, but the more information one gathers, the better it can be calibrated. So this is the basis for that mechanistic empirical design function. So finally, from my side, just summarizing this research project, I think we can learn a lot from the reuse of wrap. As you've seen from the previous speakers, between hot, warm, and cold, it is easier to use high percentages of wrap and cold recycling. But we need to pay attention to different details about the wrap, and that's particularly with the processing of the wrap before it's used in cold recycling. So we don't want the type of variability that's created in some environments with the on the level football playing field. Thank you very much for your attention.
Now we are having the last presentation in the morning, Economic and Environmental Benefits of Cold Recycling. This presentation will be presented by Dr. Eshan Dev. Just a second. Dr. Eshan Dev is assistant professor in the Department of Civil and Environmental Engineering at the University of New Hampshire. Eshan's research interests focus on the use of performance-based evaluation and design techniques to prolong the life of pavements in an economical manner. Eshan is chairman of the International Society of Asphalt Pavements Technical Committee on Pavement Evaluation, secretary of the RILEM Technical Committee on Asphalt Pavement Recycling, chairman of the Transportation Research Board Subcommittee AFK 51 on asphalt modeling. Please welcome Dr. Eshan Dev.
Thank you very much. Thank you all for being here, and hopefully I'll try to finish in time here, because we'd really like, as I echo Gabriel's comments from earlier this morning, one of the big things for us as a RILEM committee with these workshops is for us to hear from you, especially from agencies and industry, as to what your needs are, and try to align our research in a way that we are developing products and outcomes that really help, that are designed for implementation and can help overall our industry. The presentation that I have today here is really focusing on some work that we are doing. It's somewhat similar to what you see or what you saw with Davide's presentation, so that's good. That will help me to go through a little bit quickly, especially when we are looking at the carbon footprinting and stuff like that. This work is really done together with two students, Katie Heslett and Shane Majenski, who are graduate students, working together with myself and Wei Wei Mo, who is another professor in our department. She's more focusing on systems engineering and sustainability evaluation and so on. Just to give a perspective where I come from, so that's the map of United States, and my home state of New Hampshire is located right there in what we call the New England region of United States. The university is located not too far from ocean. We are about 15 kilometers from there. Just a couple of images. That's the campus. That's our building, and the labs are down here. So that's where we do most of the work that I'm going to be presenting. And just it's loading. Sorry. There we go. I just wanted to show a couple pieces of equipment that we have, and especially the foaming device and the mixer, because the focus of my presentation today is cold recycling. So the results that I'm presenting here are really coming from a project that we did recently where we developed cold recycled mixed designs for a company for City of Manchester, which is the largest city in my home state, to do in-place recycling for them. Sorry, it's a little slow and showing up. Maybe the batteries are dying, I don't know. So it's just a couple of pictures from that project. As you can see, I don't think I need to go into how cold in-place recycling works. When this project we were using foamed asphalt, so you have the asphalt tanker and then you have the recycler. which is forming the machine, forming the bitumen. You have your existing pavement, and they had laid down some cement. We are using about 1% of cement in our mix design, which is already placed on the roadway. But really, process-wise, it looks somewhat similar to hot recycling or doing hot construction, essentially, except for this device, which is really equivalent of your plant, that is removing the existing material, remixing everything, doing the foaming, and then producing your cold recycled mix that goes into your asphalt paver and is placed down. We can keep on going. All right. One more. There we go. So as you can see, the final product doesn't look that different than what we are used to with traditional asphalt paving, and that's really the message that I was trying to convey with these set of slides. But it's really nice in doing this project. What we were able to do is gather a lot of information, and as you saw with Professor Jenkins' presentation, not just find properties for sake of specification, but find properties that we can then combine in performance models, which are essential not just for us pavement engineers to look at how long that roadway would last, but also for planners and politicians and economists, so that we can tie back or determine what is the cost of doing one alternative versus other, and not just how much it's going to cost me today, but look at really the life cycle cost. And then try to go a step further, as you saw with Dr. Lopresti's presentation, of also looking at environmental impact. So this project really gave us that opportunity with all the material that we were able to sample and all the testing that we were able to conduct. Why cold in place recycling? I don't think I really need to re-emphasize on this. This is more for something, especially it seems that in Brazil you guys are already doing fair bit of cold recycling. For my region and the New England portion of US, it's still considered fairly new technology. There's not a lot of in-place recycling. We are doing quite a bit of cold central plant recycling, where you generate RAP, take it back to the plant, do the cold recycling, bring it back out there. So the biggest advantage with this, as you'll also see in my results, can really help you lower the cost for two reasons. One, you are not moving all those tons and tons of material from your pavement site back to the plant and back out to the site. You are really doing all of that right there in place, and that leads to tremendous savings in terms of cost, but also in terms of time. And a lot of times when we are working on these urban areas like Sao Paulo, just the traffic generated from construction vehicles to move all that material, it also has a really negative social impact. So that's another positive reason or positive advantage with in-place recycling is that lowering of construction vehicle traffic. As I mentioned before, since you are not moving the materials, it allows you to conserve aggregate and utilize everything that's out there. So you're 100% using material that's there. You can supplement with other materials, but at least you are not losing or generating another landfill by taking that RAP out of your existing pavement. So those were some of the motivating factors as to why we did this study when we did it. Just for matter of perspective, what I have there, I apologize, there's lots of bars there, but really what you need to focus on is we have 3 boxes. That is your traditional hot mix asphalt, your regular asphalt mixes that we use in New Hampshire. These are typical mixes that we use not on surface but below surface, so binder and base course mixes. And these are 4 cold in place recycled products that or mixes that we have looked at recently. Just to give you a perspective, we are simply comparing modulus of these materials. So just looking at modulus, you can see that, yes, we are looking at a lower modulus, at least with these materials that we are using. More recently, we have done some more testing where we are seeing modulus values fairly comparable to these surface courses. But you can still see, I mean, with some trials, we were able to get in the ballpark compared to what you see with hot mixes. So you're not that far. It's no longer the mindset that you are really dealing with a glorified granular material. It's really behaving, performing more like engineered hot mix that we have in our routine practice. The main difference is in order to make these mixes, you need a regular plant, a full paving operation. These four, you are really doing that construction train approach where you have the recycler and the paving happening all at the same time, as opposed to having this full hot mix plant. More properties where we are looking at some cracking indices. Obviously, that's not something that's a big concern with cold recycled mixes. These are typically covered up or placed with overlays on top, or at least in general, our experience has been not too much of issue with cracking, partly because we don't use much cement in our cold recycled mixes, if any. I mean, a lot of these trials, you can see the CM1 mixes had no cement in them. The CM2 mixes are 1% or lower, and 1% is probably as high as we would go. So usually we are not as concerned with cracking, but nonetheless, for documentation purposes, if we compare them, you can see that, again, they are looking somewhat similar to your hot mixes. So it's helping change the mindset that we are dealing with a more of a low quality material. That's not true anymore, and it's important to realize that. Life cycle cost analysis and life cycle assessment, two different terminologies that I'd like to introduce here. And the reason for them is essentially what I mentioned at the start of my presentation. Our traditional pavement design and material selection processes have been driven predominantly by economics, and mostly by economics of right now. In other words, if I am doing 1 kilometer of roadway this year, what budget I need? And I think gradually as an industry, we are realizing that that's not the correct mindset. What we need to look at or start to look at is what's going to happen in 15 years, 20 years, 40 years, 100 years, and try to make decisions same way we make decisions when we purchase a car or a house, right? We don't purchase a house only looking at how much it costs me right now, but we look at how much is it going to cost me over its lifespan, and when I sell it back at the end of when I'm done with that house, what kind of money I can recover. And we need to look at pavement in that same sense. So we really need to incorporate the life cycle cost and simultaneously environmental impact side of things in managing our highway infrastructure. Life cycle cost analysis, one can think of it as a subset of life cycle assessment where it's focusing on just the economic side of things, something that encapsulates or integrates all different costs that you may have, your initial cost, your maintenance cost, your rehabilitation cost, even what do you do with the material at the end of that life. Within this, you should also incorporate the user cost, since they are the ones, or vehicle users or drivers, they are the ones that are using this facility, and that can be built into toll cost or fuel cost and things of that nature. So really it's a tool that allows us to look at all these aspects of cost as opposed to only construction or material cost on day one. And that's really the concept that I'd like to show you some results with a case study that we recently finished. Life cycle assessment is slightly bigger. In this case, you have cost as one aspect. So LCCA could almost be assumed as a subset of LCA. And Davide already went over this framework in general sense. But what we are doing is really what's referred to as a sustainability evaluation, or really looking at carbon footprinting. In our case, we tried to also incorporate the operational aspect of life cycle. So we didn't just look at carbon dioxide or carbon dioxide equivalent emissions from construction of material, from transportation of material, from production of it, from maintenance of it. But we also looked at the use phase, where we looked at all the vehicles and what kind of fuel they are using, and how roadway roughness affects that fuel, and how traffic conditions affect that fuel efficiency. So we tried to build all of those aspects into this particular case study that I'm going to show you here. It's coming. So the case study I'm showing you here is for a highway that's located in New England. It's called I-495. It's one of the loops around Boston. It's one of the heaviest traffic roadway in our region. You are looking at about 128,000 average annual daily traffic. Very heavy loads, 2 to 4 million e-cells in 1 year. We're not looking at lifetime e-cells, so that's a single year e-cell measure, so quite heavy loads. And what we tried to do was use that particular roadway or a stretch of it that's about 22 kilometers long as a test bed to try out these different technologies and these different type of approaches in making recommendations for different materials, different maintenance strategies, and so on. As you can see here, what we also tried to do was incorporate the traffic conditions. So we did not assume that everyone is always traveling at 60 kilometers per hour on these highways, because a lot of times there's very heavy traffic, very heavy congestion, as you guys are very familiar with here in Sao Paulo. So we tried to do the same thing where we build that traffic side in our analysis. That's just a big picture. I'm not going to go into every aspect since we don't have a lot of time, but it really shows the framework that we have developed and have been using. I'd just like to point out at two things here. One, we are using a tool that was developed by Environmental Protection Agency in the United States. It's called MOVES, which stands for Mobile Vehicle Emission Simulator. In other words, this is a tool that is developed by automotive engineers that can actually take into account different type of vehicles, age of vehicles, your climatic conditions, roadway conditions, and really predict what kind of mileage or what kind of fuel efficiency you would get, and for those fuel efficiencies, what kind of emissions your vehicles are generating for all of those factors. So it's a very comprehensive tool, and that's what we have adopted here to bring in the operation phase emissions. The other side I'd like to re-emphasize is what you heard from previous presentations. In order to do any of these things, it's extremely critical that we have relevant material properties. We need to have performance properties that are, again, not just a way to specify material, but also to be able to predict into future what would happen to those materials and how they would fail and how they would evolve, and then provide us with options as to what we can do in order to fix these type of systems. The overall study included, it's quite extensive. We are looking at 5 different type of pavements with 5 asphalt mixtures and 6 different maintenance approaches. So overall you can see a lot of different combinations in the study. These are typical mixes that are used on these highways. So we had properties of them. And that's the cross section. You can see fairly stout or fairly thick cross section, but that's not a surprise given such a high traffic level. Again, keep in mind 2 to 4 million e-cells every year. So you're looking at extremely high traffic volume. In terms of maintenance, we are looking at really 5 different alternatives and different combinations. Something as simple as crack sealing, a couple of pavement preservation type of techniques, which are microsurfacing. I don't know if that's the term that's commonly used here, but it's, again, a fairly effective preservation technique. And then from rehabilitation perspective, we are looking at 2 alternatives: doing cold-in-place recycling, or doing your traditional recycling where you would go and mill your pavement and replace 50 millimeters of it with a new asphalt structural overlay. And again, as with life cycle assessment, you have to make sure that all alternatives are compared in a fair way, which means that you have to make sure you're looking at long enough time cycles so your results are not biased. And for each combination that we are looking at, we made sure that we had full 3 cycles of its performance simulated in there. And when you do that, it looks like the scary type of plot that you have here with so many different lines, and I'm not trying to have you read through it, but I just want to show that what you get as an outcome is how your pavement roughness, as International Roughness Index, is changing with all these different combinations over long durations of time. That then we can put back and look at different costs and different environmental aspects. And so really the final objective is this. What we are looking at here is just the cost on part of the agency that's maintaining that roadway. 4 different strategies we are able to see in terms of net present value, so it's time normalized, you put in interest rate, inflation, and everything else. But to maintain that stretch of roadway, what you are looking at is dollar amounts, and again, it's shown in terms of color coding, where these are the cheaper alternatives. You can see that the cold-in-place recycling was really shown as a very promising alternative, and especially at much lower cost compared to some of the other baseline type of scenarios. You are seeing substantial savings just on part of agency. This is not including the user costs, which were also fairly low because your pavement roughness is fairly low with the alternative that we were using here. Again, very busy plot, but what I'm trying to just focus on is the global warming potential. It's similar to what you saw with Dr. Lopresti's presentation. This is shown in terms of gigagrams of carbon dioxide equivalent per year. The green part, he mentioned hotspot was really in the production. I would say hotspot for pavements is really in the use phase, because vehicles that are using the roadway are the biggest contributors of greenhouse gases. Compared to that, you can see that the other maintenance and construction activities are fairly small, but nonetheless, they are still substantial. And what we were seeing again is that with cold-in-place recycling for these different types of pavements was always near the low end in terms of its footprint, with as much as 88% difference that we were seeing with some of these cases with using cold-in-place recycling as opposed to other alternatives. So this really gives us confidence that not only you are going to save money, but you are also doing something that's helpful in context of overall environment. So just to conclude things, first of all, life cycle assessment is really a good tool or good way to look at things in terms of overall big picture. Again, not looking at today's investment, but looking at what would happen to this roadway over its lifespan. And this is not surprising to you guys, I know this, but when I show this to some of the agencies in my region, they still think that cold-in-place recycling is technique for low-volume roadways. That's the general mindset. But our research is showing that that's not true. I mean, you can do these good engineered cold-in-place recycling systems that can work on very high-volume roadways. And so we are trying to change that mindset and have them be more bold in using these technologies. And as you have seen throughout this morning, there are a lot of ongoing efforts on recycling in general and specifically on cold-in-place recycling, especially in U.S. I think there's more and more agencies doing implementation studies, as well as developing tools for quality control, quality assurance of these materials. And then finally, I think where there's most need is more and more performance testing and modeling of these systems. As Davide mentioned earlier, it's interesting to also, or important to put in the durability side as well. We should not assume that all materials would perform or will have equal durability, and this will allow us to determine that. So that's my last slide. The only other thing I have is we are putting together a webinar through RILEM committee on life cycle assessment. This one is focused on pavement LCA with emphasis on recycling. It's a free webinar. I've asked Camila to send out information about it to all the participants today, so you will get an email from Camila about this. But we really hope that you can join in this webinar and get a little bit more background on the LCA side. I don't think I had enough time to do justice on what all things these type of approaches can do, but I hope that this will allow you to get more background. So that's all I have, and hopefully we are not too late.
I would like to thank all the presenters for today's workshop, and we would like to welcome you back to the stage for the roundtable discussion.
Gente, acho que agora é uma boa oportunidade, né, para a gente discutir um pouquinho sobre o que foi apresentado, sobre as nossas práticas de projeto, de técnicas construtivas. Então, podem fazer a pergunta em português, eles vão estar com o tradutor, tá? Não fiquem envergonhados. Por favor, quem for fazer a pergunta, se apresenta, tá? E, por favor, somente no microfone para que possa chegar lá na tradução simultânea. Vai ter um microfone desse lado e um outro microfone com a Diomária e outro lá. Então, são 3, tá? Kim, tá faltando cadeira.
Good morning, everyone. My name is André Cazu. I'm a master's student here of the University of São Paulo. And actually, I have a question for Professor Gabrielli about the presentation of cold recycled mixtures. I've read some papers talking about the increase of stiffness when cement is used even in a low content, even with 1% of cement. So my question is, if cement is not used for the increase of stiffness of the mixture, why not using other mineral fillers that are cheaper than cement in order to properly disperse the bitumen?
So the main point, as I showed, one of the points of the active filler is to provide something with high level of air voids to be able to carry the bitumen. And cement has a higher level. Even lime has even more air voids. So lime can be really useful. The other let's say action made by the active filler is also to keep in account how to manage the water, the amount of water inside of the material, because the water is one of the components of the emulsion to carry the bitumen and the foaming process. But because it's a granular material, we need also the water to have the maximum density and to have the compaction. But after that, we have to remove the water. So the active filler works in that sense. So basically, there are several options. There is cement, slime, fly ash. So the key point is to have something that has a high level of air voids. Basically, for what I know, maybe Kim can be more precise. In the past, people started with lime, but was more easy to find cement, so they moved in the cement as an active filler, just to keep in account that it's much more easy to have the supplying of cement. But yeah, the point is that in the bitumen stabilized material, we don't need this kind of material as a binder. We need as for other effect. Yeah.
Absolutely agree. And maybe just to add one or two other aspects. Right now, we recommend that people consider different active fillers for the cold recycling process. So to look at both lime and cement. With cement, you must be careful because, and this is the mindset of people, if they are chasing high RTS results, the more cement you put in, the higher the RTS. But you're building rigidity, brittleness into your layer, and you're going to then get cracking. Then it's not a deformation type of design. The other two aspects, just to add to what Professor Gabriello was saying, the active filler, whether lime or cement, you can work out which one works the best. assists in two other aspects. The one is the bond of the bitumen to the aggregate. That bond doesn't happen naturally in the mixing, because it takes actually the compaction. If you take a mix like foam bitumen, where you've got discrete little droplets, you've got water, and the surface energy tells you that the water's got a better affinity to the aggregate than the bitumen and the aggregate. So the bitumen has to have some sort of a partner to create that adhesion to the stone. That must either be the compaction or the chemistry of the active filler. And where you see it is you'll see it in your wet conditioning tests. And if you leave out the active filler altogether in a dry condition without any exposure to moisture, you can get good results. But as soon as you expose the mix to moisture, you will see the amount of drop-off of the shear strength, for example, is dependent on the active filler. So it disperses the binder, but it also plays a vital role in resisting moisture damage.
Professor Jenkins, good morning. It's a pleasure to have you here. I just want to add something about his questions. Says, if you want to keep in stock, the BSM in stock, you better use lime, okay? Another thing is, in some countries in South America, you're not allowed to use lime because of drug problems, okay? So you can only use cement. So you have to choose whatever you have in your hand, okay? And you focus your presentation on grading, the grading problems, okay? Not problems, but the grading characteristics. How important do you consider crushing the material or crushing wrap, not to break the aggregates, but to break the lumps on in-plant cold recycling? Thank you, Professor.
Thank you, Mr. Cipollino. This is another important question. Yes, first of all, I entirely support you. If you are stockpiling, it's a cold mix, so it can theoretically be stockpiled, but you would prefer not to use cement in your mix if you're stockpiling. Lime would be a better solution because it doesn't set up while it's in stockpile. It remains more flexible. In terms of the crushing approach, this is, maybe I didn't emphasize it enough, but this is very important in the processing of the wrap before using it specifically in cold recycling. You don't want to crush the aggregate of the original asphalt. And this is where an impact crusher is very useful. If you look at alternatives like cone crushers, they tend to force the wrap together so you don't break up the lumps. Basically, you want to try to separate the original asphalt into its major components that can give you a good continuous grading, but you don't want to crush the aggregate. And this is where crushers like impact crushers, which just actually knock off and separate these lumps into their individual particles, not down to the very fine fraction, but smooth enough to give you the right grading. These sort of selections are very important in using the process as a pre-processing tool. And it's something that we've realized. If you want consistency out of variability, you need to process the wrap properly before you reuse it.
Armando Murilha, parabéns a todos pela apresentação. Eu tenho uma dúvida mais conceitual com relação à utilização de particularmente emulsão asfáltica na reciclagem. No Brasil, nós temos uma tradição relativamente, vamos dizer assim, razoável, de utilização de espuma de asfalto para gerar bases de pavimento. Tá? Na questão da utilização de reciclagem com emulsão asfáltica, eu tenho uma dúvida em dois aspectos. Se for utilizada como revestimento, reciclagem com emulsão como revestimento, duas ponderações. Primeira, a questão da cura da água, da emulsão, às vezes água de amassamento, que talvez tenha. né? Então, essa é uma questão que impede, muitas vezes, que a reciclagem seja feita em altas espessuras. E a outra questão que eu acho mais importante é com relação ao volume de vazios da mistura asfáltica reciclada a frio, quando utilizada como revestimento. Normalmente não se consegue níveis de vazios abaixo de 5%, 6% como revestimento, e isso preocupa com relação à entrada de umidade, que o pavimento não tem que ser só resistente, tem que ser impermeável na medida do possível. Essa era a questão, eu não sei para quem, acho que para... Obrigado.
I can try to start to answer. First, let's go with the last part about air voids. Usually in cold recycling materials, the air voids are much higher than in HMA. It's usual to have above 10, between let's say 10 and 15% is usual. That makes those materials more sensitive to moisture. That's a fact. In North America, at least, it needs to be covered by something. It can be a hot mix, it can be a microsurfacing, a chip seal, or something to make it waterproof. Okay, so that's a fact. That's something that we know. It will remain hard to compact material because of degradation, because of the bitumen that's put in. The water is there to help, but it's not magical. There's a limit to what we can do. And when you said that the thickness has an influence, you know, if you have emulsion in it, if I understood right, you mentioned that you're afraid that if it's really thick, the emulsion will not cure or break or something like that. It's possible, yeah, all right, okay. So it's possible. And if we look, at least I would say in Canada, in my part of the world, if you do recycling with emulsion, it will need to stay open to traffic for at least 2 weeks before you can cover it with anything. If you do recycling with foam, you leave it open for 3 days. Okay? So we know it takes a lot longer with emulsion than with foam.
Another consideration with this concern about breaking and curing, as we know, there are a number of aspects that will influence it. The temperature of the aggregate, the temperature of the emulsion at the time of mixing, as you say, the thickness of the layer. Another one that's very important is the moisture conditions of the existing layers that you're going to treat. And we've been talking primarily about RAP, but in many cases with emulsion used in recycling, you've got a combination of RAP and virgin aggregate. What we've seen with, and these are very practical aspects you're asking about and commenting on, what we've seen with various projects, the field moisture content, the content of moisture in the field, if that is close to optimum moisture content, and you come with emulsion, with the emulsion you're adding 40% water into that layer as well. You're going to get mixing, but one, you're going to have more difficulty achieving your compaction because now your fluids content is going over the optimum. And the other thing is you're going to have a slower breaking time. And this is where you can pick up, if you've got a 30 centimeter layer, breaking in the top 15 centimeters, but the lower 15 centimeters, you can open up some projects in various parts of the world. And some months later, and sometimes even longer than that, the bottom half hasn't broken and certainly not cured. So the in situ moisture conditions are very important in your selection of technology. And with foam bitumen, you're not adding any extra water. So if you're close to OMC, you can just apply the foam stabilization technology and you would not have the same sort of problems.
And also the selection of the roller compactor is extremely important. If you have to do a cold technology with water, it's extremely important to have the wheel compactor, because if you have only the steel one, you don't have the shear that allows the water to come out. So this is an important detail. So you have to use the proper compaction and be careful also because the people easily, not in Brazil but in other countries, I had the problem with people that was talking about emulsion and everything was emulsion, but it's important to use a proper emulsion for cold recycling, not a general emulsion, something that is specifically designed for this kind of operation. And but the compaction, the wheel roller compactor can make a huge difference in the compaction effort and in the way to take out the water. Generally speaking, in Italy we cover when we have the moisture content of the layer that reach the 50% of the optimum moisture content. So we have a reduction of the 50. You can go on the top to close that, just to give a parameter.
Just to add one more thing, I think Gabriel mentioned that already, but the light's on. So just especially on the emulsion side, and I'd like to mention that because that's area where in US right now there's extensive research. The emulsion formulations have improved substantially. There's a lot of chemistry that goes into it. And we are at the point where a lot of larger companies are taking samples of wrap and really doing some trials in lab to come up with formulations that are designed in terms of how thick of a layer that you are going to recycle. And also to some extent, as Kim mentioned, one thing that's always uncertain with emulsion-based recycling is what is going to be your weather or rainfall in the week after construction. So that plays a substantial role in what happens in terms of the movement of moisture.
It's me again. By using emulsion, we have to transport water, we have to cure, and the final asphalt content will be the same with foam. Technically speaking, why use emulsion, Professor Jenkins, or Professor?
One clear advantage between these two technologies, and both of them have their benefits and disbenefits. There's no doubt about that. There's not just one solution that's perfect for everything. Is emulsion, as was explained earlier, as we know, it's used for paint that we have on the walls. It coats things very nicely, the emulsion. And it does that with the aggregate. So in terms of waterproofing the layer, there is a benefit from the emulsion in terms of its dispersion and the resistance to moisture. It does, as you're suggesting, generally come at a cost because litre for litre, 1 litre of bitumen that goes into foam is approximately a similar price to 1 litre of emulsion. So you're paying for 40% water. So that is more expensive, and as you say, you're transporting it. But there are benefits in terms of the waterproofing that it can provide. Another small benefit is, in some cases, with a coarser grading, the emulsion as a binding agent is less sensitive to the lack of fines in the material. It can still coat without having as much of the 0.075 and the 0.425 fraction, although you still need some filler in your mix. Yeah, back to grading issues. Sorry.
Rodrigo Vasconcelos from Copavel. I'd like to thank you all for coming by to Brazil and thank the professors of USP, Liege, Camila. It's very good and very nice to have you all here down to in this industry workshop. It's very good for us to learn directly from you instead of from the books. And one thing I'd like to point out when we are designing recycling project is you all talking about the mixture itself, the recycled mixture, and the performance in the field always depends the support we have underneath. And I haven't seen any procedure or method that we address because we have at least we must have a good support to have a good performance. So I would like to explain us a little bit more about this because it has a huge impact in how the pavement will perform in the field in recycling projects. For instance, in cold recycling projects.
I think that we are talking about a rehabilitation operation. So first things is extremely important to really understand what is the damage that is going on in the pavement. So if we have something that is related with the subgrade, we cannot think that we can solve the problem of the pavement only working in the surface layer. So we have to remove, we have to stabilize the subgrade or solve the problem of the subgrade and go up. So it's important to design the maintenance. A maintenance job is a maintenance project. It must be designed as like a new pavement. So you have to strongly consider what are the conditions of your subgrade, if you have enough the building capacity, and if the damage is made only by the fatigue related with the vehicle, or if there are problems related with the pavement structure. So it's a comprehensive approach that gives you this, the solution of that. So don't make the mistake that if you have a rotting or something like that, you can solve the problem simply reconstructing the pavement, because if the problem is in the subgrade, you have just made some maquillage, but you don't really solve the problem of the building. And one of the problems is that in several cases you have a rising of fine particle in the aggregated layer. So before to move forward, you have to solve that. So you have, okay, it's something that the agency doesn't like so much, but they don't like so much, but you have to open all the pavement, goes down, solve the problem of the fine raising, compact the subgrade, and reconstruct. In this case, you have enough strength to have the proper compaction, but also you solve the problem of the pavement. And there is not a guarantee that the whole pavement has the proper thickness to support the level of the traffic. So you have to do a design. So the key point is design globally your pavement maintenance approach, and after that select what is the best condition.
Rodrigo, if I can add to that, that's a very important question, because today we've been focusing on hot, warm and cold mixes, the upper part of the pavement, but so important to understand what it's sitting on. And I think Brazil has been very successful in a number of projects that I've seen here in doing the right investigations, doing FWDs, doing DCPs, doing test pits, and then combining that information to get a good understanding of what profile you've got in the existing roads, and then basing that for the designs to see, okay, what deformation can you expect, what tensile strains you can expect in the upper part of the layer as a result of that support. And you can see that in the performance of some of these projects on the Ayrton Senna highway, etc., that have been properly investigated and the right principles applied. In addition to that, that's for rehabilitation, and that's a very important part of pavement engineering. Is like a doctor, medical doctor diagnoses first what the problem is before you implement some solution. The second part is for the new construction. It also links to the subgrade, is that if one recognizes you don't quite have the support that you require underneath, that cover thickness And then particularly if you're going to use bitumen stabilization, cold recycling technology, a cemented layer underneath that, so a cement-treated subbase, is a fantastic solution, because even though it does get some shrinkage cracking, if you use a bitumen stabilized layer above it, that's a crack preventer. And then you can reduce the thickness, as you've done here very successfully in Brazil, with a thin surfacing of asphalt on top and the load spreading coming from the bitumen stabilized material. But that can, specifically for new construction, be augmented by a good support underneath, where you can get better compaction and much better support for the BSM layer.
Thanks for raising the point. I think that today we're here to actually share best practices on how to recycle in this possibly, top or 2-3 top layer of the pavement, and possibly providing best practices for sustainability. But as we mentioned before, durability, it's a key concept, and there is no durability without considering the pavement as a whole. So what comes from the subgrade needs to be considered as well. And having said that, there is a real need in terms of creating best practices that goes along with all these best practices for sustainability. So again, there is no recycling without best practices that change it case by case. And an investigation on what you just raised is as important as what we are discussing today.
Mário Henrique. Alô? Mário Henrique Andrade, da Universidade Federal. Alô? Mário Henrique Andrade, da Universidade Federal do Paraná. Na reciclagem a frio com emulsão para a produção de bases, existem emulsões especiais que dizem promovem o amolecimento do ligante residual, né, o softening, e a promoção de ganho de propriedades ao longo do tempo. Então, a minha pergunta, a primeira, é se isso é fato ou promessa, e se podemos utilizar isso para efeitos de dimensionamento. E a segunda é que, até que ponto estudos de deformação para a base com emulsão ou estabilizada com asfalto, se estudos de deformação permanente são importantes na medida que não tem ação direta do tráfego e da insolação. Se isso é importante para efeito de dimensionamento, aspectos de deformação permanente em bases recicladas com asfalto.
Regarding your first question about using emulsions that have some of these additional agents that allow to soften the binder, we had some experience. Actually, the results I showed you, I had 2 cold recycled mixes, and then there were 2 more which had letter A after them, and both of those were made with a special MS4, a medium setting emulsion that also had a certain minimum amount of aromatic oil in them. That was not my choice, but that's what our local agency required, and their reasoning behind it was that it would allow us to mobilize or soften the binder from wrap and promote blending of it with the emulsion. We have constructed test sections with those in lab. I can say that, and all of this was done with 7 days of curing. After that, we did see some improvement, especially if you look at properties, specifically looking at rutting properties or cracking properties. From modulus perspective, though, those emulsions actually gave a lower value, which also makes sense because you're adding a softer material in there. I don't think there's personally, I don't think there's enough conclusive results yet to know whether that will happen or not, but at least early results to me look more promising that you are able to utilize more bitumen from RAP when you had these type of additives that were put together with the emulsion. Second question on permanent deformation.
I think that the first thing to avoid permanent deformation is to design properly the size distribution of the material. So if you are able to achieve the proper interlocking and the proper pavement structure, you solve your problem. So this is the main point. There is no other choice. Of course, if you over design your amount of bitumen, but we are not the case. If you are talking about bitumen stabilized material, we are generally put low level of bitumen, because the other problem to have rotting is to have too much bitumen. That is one of the problems in this case in the hot recycling. If you are not investigate properly the amount of bitumen, of the still active bitumen inside of the wrap in the hot recycling, putting the same amount of wrap, you can has as a result too much active bitumen, and maybe you are in the wrong side of the material. In this case, in the hot recycling, you have to be very careful in the.
I think also it depends on the kind of permanent deformation you have, because if you have a very narrow circle deformation, maybe it's only rotting on the surface layer, so it's only a surface problem. But if you have a very large permanent deformation, probably it's a problem of the bearing material. So the solution, as the question jumped to the question before, would be completely different. It's the structure you have to change. If you have a very large deformation, it will be only the surface. If you have a little deformation.
So actually I have one more question. When hydrated lime is used as an active filler in cold recycled mixtures, actually I'd like to know if there's any recommendation of the time that the mixture can be stockpiled, because as far as I know, as far as I read, the materials, they have only a qualitatively recommendation and not a quantitatively recommendation. So thank you.
There are a couple of key aspects when it comes to stockpiling of cold recycled materials. One aspect is the height of your stockpile. The higher you go, if you go above 2 meters, it's not recommended, because you create compressive stresses at the bottom that are effectively compacting the material. So when you try and reuse it, you'll find that you're going to get lumps. It's almost like building up a compacted layer type of effect lower down. A second aspect is that there is a shelf life of the material. However, with time, if you lose moisture content in the stockpile, and this is where climate comes in as well, because obviously there's high void type of situation in stockpile. If you lose the moisture, you don't have the mobility of the bitumen particles to find their right positions in dispersing in the mix that happens during compaction. So you've got to keep either a tarpaulin over your stockpile or some sort of protection to keep your moisture content in the mix. These are important aspects. Generally, I mean, we've had projects where after 2 or 3 months the materials laying in stockpile and can be reused. You're not going to get 100% of the same resilient modulus that you would have got with a fresh mix, but you will. It's a sliding scale, and that's why people don't recommend design for 80% of your stiffness modulus or whatever. It's going to depend on climate, the time factor, etc. But that's something one would have to work out. It's not recommended to go more than a couple of weeks in stockpile, but if you're forced to, I would make an adjustment in your design of that layer. You're not going to get the full performance of the mix.
Professor, on a contractor point of view, I think we have to make, my opinion, okay, to make very clear the difference between the stackability of wrap, foamed wrap, on a operational concept or an academic concept, okay? If you're a contractor and you leave your wrap 3 months foamed there, you have big problems, or on your job site, or you don't know how to manage your job, okay? This stackability helps us as a contractor to plan the job, okay? But these things about 3 months, this is academically only, okay? If you leave 3 months there, you're broken, okay? That's my opinion as a contractor, okay?
So from my personal point of view, the chance to put in a stockpile the material is something that can help you. It's like the security wheel is something that you can do. But basically, I think that if you don't have a specific reason or something that forces you to do that, or so, it's better to plan your work, to lay down the mixture as soon you have compacted or very soon. Of course, maybe you can have a heavy rainfall or something.
Sorry to interrupt this session, this discussion session, but they have to go to Guarulhos to take a plane to Fortaleza. Sorry, everybody. And I'd like to thank you, everyone, for coming, and our invited speakers. Thank you very much. Have a nice day.